Okay, so in the previous lecture we have learned that when we have a short channel device, the threshold voltage of that short channel device its threshold voltage is small lower than that of a long channel device. So even at zero drain voltage, we had the roll up of threshold voltage. So Vt roll off, it means that if we reduce the length of our transistor, then threshold voltage can be reduced. So this is a short channel area. So that was happened even even when we have exactly the value quite close to 0 volt. However, in this slide we are now talking about a phenomena called as Dibble, drain induced barrier lowering, and this is a Dibble. Dibble is one of the most important quantity in our technology, not for improving our performance, but this is the degrading factor of our performance. If Dibble is too high, then we think that the show is stopped. Show means that the scaling of our transistor technology. So this is the limiting factor of our technology development. What is a Dibble? It is measured in that way. So think about a certain value of a relatively low VDS value. So in this case, of course, the threshold voltage we can achieve for this device, if this is a short channel device, then the threshold voltage, the one by a short channel device, would be a little bit lower than that of a long channel device. So please think about this one. If we have an ideal long channel device, then we will have a certain value which is corresponding to a long channel device. And if we just reduce the length of our transistor, then obviously we will have a reduction of threshold voltage. That was introduced in our previous lecture. Now the length is fixed, and only difference is even for a single device, now we apply even higher drain voltage, and we find that, wow, so threshold voltage is reduced even further. Maybe you can ask me this question. Well, compared with this relatively small VDS value, so now we apply much higher drain voltage, like 1.2 volt. So it is quite much acceptable to have higher drain current. Since we applied higher drain voltage, higher drain current, it looks quite reasonable, but it's not that much in this case. So please note that here we have the region called as a subthreshold region, and in this case our drain current just follows the rules like exponential VDS scaled by summer voltage. That is the rule for our 1 minus this one. Here we have a certain factor. So if we have sufficiently high drain voltage, then actually that value should be just approaches to a given value. So the one we can find in this case, there is almost several times difference in its magnitude. This is not unusual one. We can not expect this kind of behavior. So this kind of huge difference in the subthreshold current can be explained only by the reduction of threshold voltage. So please think about these three cases. So we can think about ideal long channel device. In this case, threshold voltage is just the same for low VDS and high VDS. This is the highest one. And think about short channel device. However, let's say VDS is quite low, then we will have a certain threshold voltage relatively smaller or lower than this long channel value. And for same short channel device, if we increase the drain voltage even further, then we will have even further reduction of threshold voltage. Double means this step. Double just consider the additional reduction of short channel threshold voltage only due to the application of an even higher VDS value. So what we can do is like this. Just to measure drain voltage at low VDS condition, and also measure once again same threshold voltage at relatively high VDS condition. Please note that when you apply low VDS, you will have a higher threshold voltage. So the order of the difference should be done in this way, not the other way around. And that is normalized by our high VDS minus low VDS. That should be calculated to quantify our Debye quantity. So let's just do the math for this simple case. In this case, let me just estimate, well, in this case, if we have this one, and here we have 1.2 volt and 0.05 volt, then I would say, well, for example, 10 to the minus 6, 1 microamp per micrometer is regarded as the criterion for detecting threshold voltage. Well, why we have to take this value? It depends. Actually, depending on your definition, you can say that, oh, this value is the criterion for selecting your threshold voltage, or you can try this one. Of course, if you select it in that way or the other way, well, it's a physical justification would be quite difficult. So anyway, depending on industry convention, we have some numbers, and more or less that condition, 1 microamp per micrometer is regarded as the value for our threshold voltage. So then in this case, for relatively low VDS value, what we can say is around 0.31 or 32 volt would be the value for threshold voltage at VDS equal to 0.05 volt. Well, now if we increase our drain voltage up to 1.2 volt, if everything is ideal, then actually we have to have exactly same value, but in reality now we have strong reduction of our threshold voltage. Well, let's say in my estimation, I would say it's like 0.25, for example. Well, in this case, if we have to calculate the difference, it means that, roughly speaking, 0.06 volt difference occurred by changing our drain voltage. but the amount of drain voltage, the change of drain voltage was 1.15 volt. Now you understand the difference between these two numbers. So just to calculate their difference to quantify this Dibble value. So well, the value is not that exactly matched, but please believe this value. When I draw these graphs, I just measure the exact value and calculate it. So 45 millivolt per volt, that is quite acceptable value for our technology. So typically speaking, the worst value we cannot endure any further is just like 100 millivolt per volt. That is regarded as a very bad value. So if we have a certain 10 millivolt per volt as a Dibble, then well, we say that it's acceptable. So which one is a good number and which one is a bad number? So if you have as low as possible, then you will love it. But well, but it is difficult to give you a concrete number for best criterion for Dibble, but we wanted to minimize it. At least that is boundary for endurable or not endurable value. So it means that 45 millivolt per volt, this is not best one, but not the worst one. So we can try a little bit shorter transistor length for given transistor technology. That is the key. So of course, if we increase the length, then this Dibble value will decrease drastically. So typically, what you get from your technology is like this: draw Dibble as a function of length. Then, if you have a certain value, length value, then Dibble is really negligible. So negligible means that not exactly 0, but its value is quite small. Only after that, so we have a rapid increase of our Dibble value. So if is, for example, let's say that 100 millivolt per volt as a criterion, then this Dibble value will exceed this criterion. It means that that value can be regarded as the minimum value we can endure with given Dibble criterion. So then what should we do? Actually, there is not that much thing to do. So if we have this problem, then this technology is just over. For given technology, you cannot reduce your gate length any further. So of course, you can try to change details of your technology. Then maybe you can slightly improve. What is the improve? Improve in this case means that you can reduce your graphs, Dibble graphs, like this. Wow, previously you had a certain L mean value, but just to push your curve toward the left side, then you can just decrease the minimum length of your transistor. Then of course, since your current is proportional, or your drain current is proportional to this factor, width divided by length, if you can achieve even shorter minimum length scale, then you can increase your drain current. So depending on this one, depending on this relation. So simply speaking, in order to maximize your own current, your usual task is to find out the minimum length scale which can maximize the own current. However, when you try that job, eventually the Dibble will stop this kind of scaling property. So, well, when we reduce further, no, since dibble is so high, so you cannot use it any further. So then maybe you can ask me this question. Well, why we have to be careful about dibble? Dibble, according to dibble, we will have a reduced threshold voltage. Well, now we understand, compared with its long channel variant, now we have a relatively lowered threshold voltage. As much as we understand this phenomena, can we use it for our circuit? Problem is, this dibble is really depends on the bias condition. If it is bias independent, then with this reduced threshold voltage, maybe we can play with it. But point is, this transistor is not solely determined by gate voltage, but drain voltage also makes a certain contribution. That is quite a bad thing. And another thing is, when a technology is quite weak against dibble, it means that now this technology is approaching to its extreme for its normal operation. If there occurs any kind of variation in the real fabricated transistor, then your transistor will show quite a big difference in the threshold voltage. Please think about this one. What does it mean? So, if you have quite a long channel device, then even though your length scale is just fluctuated by some mismatch of your fabrication process, your transistor just shows the same threshold voltage. But if you are working with the technology regime quite close to minimum technology, minimum length scale, then let's assume that due to the misproduction, so your length scale is relatively slightly reduced or increased. Then what will happen? Although you thought that this transistor has a certain kind of property, but a slightly longer device will show different behavior, and also slightly shorter device will show quite different behavior. So it means that if you are working on technology quite close to the end of its scaling, so minimum length scale, then it becomes really sensitive to the fabrication mismatch fluctuation. So then that will make a quite wide distributed behavior of your transistor performance. So it means that you have to fabricate your transistor. You have to fabricate billions or 10 billions of same transistor in a single chip. And if they show, all of them shows much widely spreaded properties, then there is no hope to have working chip for our given design. So that's the reason why we are so afraid of this dibble phenomena. We have to minimize this dibble as much as possible. So therefore, it is really important for even to us, the contemporary engineers. It means that, well, up to now, the history of technology scaling is like this. Well, we wanted to reduce something. If we have a next generation, so-called next generation technology, then we invented a way to control dibble. So since dibble is controlled, so our ion was increased. We were quite happy, but at once everybody can produce this certain technology level, then the competition becomes so severe. So a certain company try to make an even better transistor. So the way is, of course, to reduce even further the length of our gate. However, of course, Dibble makes the problem. So in order to solve that problem, they have to find out different ways. And usually, if they found a solution for that problem, then we can achieve once again enough to control Dibble. Then we can even increase the on current further. That was the situation we have done. And in this case, please think about the history in the last decade. So 2010. What happens in that case? In this case, what they have done was just to at the time, so they had the technology called as FinFET, and this blue region is corresponding to the silicon channel, and this silicon channel is actually covered by this. This is corresponding to a gate metal. So that was the technology we had in our former time. And after that, what was our knob to control the Dibble? The knob to control a Dibble was controlling this thickness. Here we have a certain thickness, and by reducing this thickness, we achieved the ability to control Dibble. Simply speaking, I wanted to say it this way. If you have this device will be quite weak against the Dibble phenomena. However, if you have another device whose cross section just looks like this, then this device will be much robust to the Dibble. So what is the difference? Simply the difference is reducing the thickness of this silicon body called as a fin. So by reducing this one, we can increase the Dibble immunity. So by reducing this narrow and even narrower device, we were able to make this quite good Dibble property. But unfortunately, how can we define this thickness? What was the rule to define this thickness? It was like this. We just make a pattern. So this let's say that this is photoresistors. This is a photoresistor which is used as a hard mask. After that, we just etch the exposed silicon part. Okay, this part is etched away. Etch. Once again, if we make a deep etch, then we will have the deeply etched silicon part. So now let's say that the lead part, previously silicon, is now gone. After that, this PR is just stripped away. Then now what we have is just given as this black surface. And now you can see that the thickness of our silicon fin is given as this one. This is corresponding to a fin of our transistor. So what you can see is the minimum thickness of this silicon fin is actually defined as the length scale of PR pattern, photoresistor pattern we can make. So in order to reduce its pattern, we have introduced UV. But anyway, controlling this thickness is quite difficult. Let's say that happen to be, for example, let's say 5 nanometer is the thickness, and if we have a slightly wider one or slightly narrow one, like 5.5, 4.5, what will happen? Since our ability to control debris is really depends on this thickness, so if there occurs a fluctuation of this device thickness, so how can we make a fluctuation of this thickness if our pattern, photoresistor pattern, is not perfectly uniform? If someone is slightly wider and someone is slightly narrower, or if our etching is not perfect, so some part is etched a little bit further and some part is etched a little bit less, then we will have fluctuation of our silicon fins that will introduce eventual fluctuation of fin thickness, then that is directly affecting the properties of our transistors. So that is quite a big problem. So that's the reason why people really enjoyed to reducing this thickness. So every day, every technology, they just reduce the thickness of a fin, and thin and tall, that was the trend. So eventually we have a very thin and tall fin. Why we need tall fin? If we have a tall fin, actually from the viewpoint of this top view, well, we are currently consuming the same amount of silicon area. However, compared with the relatively short pin shown here, say short pin, we can actually increase the effective width quite significantly. So let me just give you this question. Let's say that this is a relatively tall fin and this is a relatively short fin, and we wanted to introduce gate metal. This is gate and this is gate. So what happens? In this case, the effective channel is just given as the length of this length and this length and that length. Well, it's not that long, but in this case, the effective length becomes this length and this length and this length. Which one is wider effectively? Of course, this one is much more wider than this short fin. However, the aerial consumption is the same. From the viewpoint of a top view, let's say that this is a wafer top surface and this is a wafer bottom surface, and now we are using the same length scale, but inside it we have a much wider device. So then, well, it's like just a magic word trick, but it really happens in our case. The only difficulty related with this tall fin is it is difficult to fabricate it. So as much as you can fabricate it, you will love this tall fin. However, let's say that, oh, I love it, so therefore why don't you make it just 1 to 100 aspect ratio, then we can have super strong, super powerful transistor. Yes, you can try, but eventually your device will have zero yield, because your tall fin eventually collapse or merge to each other. Well, that will be a nightmare. So that's the reason why they have a certain um, limitation of this aspect ratio. But anyway, the trend was narrow and tall fin, and eventually we have arrived at the end of our fabrication capability to control silicon thickness. So now, even for most advanced fab, we cannot control our fin thickness any further below a few nanometer scale. So that's the problem, because this length scale is so important, but we cannot control it. So what we just do is just to run throw a dice and see the number 05, 06, 4. That never works for chip industry. We have to have perfect control on the silicon thickness. So that was the situation in the previous decade. Of course, we really enjoyed this kind of transistor scale. So that's the reason why we have, for example, 14 nanometer technology, 10 nano, 7, 5, 3. All of them are corresponding to this FinFET technology. But now we are at the end of this technology, and we cannot reduce the thickness any further. Okay. So anyway, well, that was just scaling tendency. And up to now, in the previous slide, we have just observed the threshold voltage even further reduced when we increase the drain current. Why that happens? So please have a look at this one. This graph just shows the conduction band energy, and now it is already this guy and that guy, both of them are corresponding to a short channel device. They have the same length scale. So it is nothing related with even further length scale, only bias value, voltage value has changed. And please have a look at the difference of a conduction band profile. When we have 0 voltage, then from the viewpoint of electrons residing at this point, they can see the maximum energetic barrier as a energy difference between this top of a barrier potential energy and its initial or equilibrium potential at this source side. But when we have drain voltage equal to VDD 1.2 volt, then you can see that actually the maximum value is not as high as the one at 0 drain voltage. So simply speaking, by increasing VDS value, we now have the reduction of maximum EC value. So the reduction of this maximum EC value simply means that from the viewpoint of electrons in source side, the barrier, channel barrier, seems to be a little bit easier to overcome. So it means that we will have more current for this case. So that's the reason why we have additional threshold voltage reduction called as DIBL. Okay, so up to now, we just spend our time to um, qualitatively understand two different phenomena related with threshold voltage roll-up. One was a geometric factor. If we have quite a short channel device, then even at low VDS value, we have threshold voltage reduction. And for that short channel device, when we further increase the drain voltage, we can observe even further reduction of our threshold voltage. So they are really cross connected. It means that if we have a long channel device, then even though when we apply quite a high drain bias, we never expect dibble. Even only when we have a short channel device, then threshold voltage really depends on our VDS value. And now we understand why it happens, and how can we quantize its value. So the remaining lecture in today's session is devoted to some certain simplified analytic expression for estimating this phenomenon. So dependence on length scale and drain voltage, both of them are considered in this simple analysis. Of course, I'm not saying that this is perfect and exact, but this provides us a good estimation about how can you understand their functional dependence on threshold voltage. And frankly speaking, well, so frankly speaking, even nowadays, researchers in this field are fabricating and writing similar papers quite a lot and submitted to the research journals, and they are sick of it because today we will try to find out certain way to how can we understand short channel effect. And since this is too important, so when we have a slightly different geometry, every time researchers make their own model for this new geometry. It means that for this device, they make a certain model, different model, then submit that paper. Well, of course, depending on the geometric variation, they really have different trends. However, that difference is not that much, frankly speaking. But every day they are fabricating, producing quite a similar paper, and as an editor or reviewer of a journal, that is quite a headache. Okay, so I will just show you the planar MOSFET case, but our eventual goal should be, for example, double gate or even nowadays nanosheet. But today's lecture we will not consider this one, but please keep in mind that our current technology is somewhere around here. So first of all, we have to understand what is the governing equation of this problem. What we wanted to do is threshold voltage fluctuation. So threshold voltage is now reduced. Why it is reduced? Simply speaking, when we have a certain gate voltage at a long channel device, we have a well-defined value of surface potential. And when we have gate voltage equal to threshold voltage, what we can have is now surface potential is quite close to 2 times band bending. It's 2 times of bulk potential. So therefore, the polarity is now inverted, and now we say that we can find the same amount of electron which is corresponding to the doping level, acceptor density. That was the situation in our long channel device. Then why do we have this reduction in the threshold voltage? Is at a given gate voltage, in a case of a long channel device, happen to be, let's say that surface potential is given as a certain number. And now when we make a relatively short channel device, then inside our transistor, now we can find that surface potential is not equal to that of long channel device. It has a little additional values in threshold voltage. Oh, so surface potential is slightly higher by amount of this capital delta. It means that even though we have same gate voltage, but in this short channel device, our electron density is relatively higher than that of a long channel device. So simply speaking, this delta is corresponding to the change of our threshold voltage. Of course, we should be a little bit careful. Change or difference in our surface potential is not directly corresponding to the shift of our threshold voltage. They have the exchange rate. What is the exchange rate? The exchange rate was called as M, you know it. So M was given as 1 plus WDM plus 3 times Tox, and this value is the ratio between our gate potential change and surface potential change. For example, let's say that if this is 1.3, it means that although we have changed our gate voltage by amount of 1.13 volt, but surface potential change will be just 0.1 volt, because additional 0.03 should be used to change this substrate capacitance. Okay, so we have to be a little bit careful. However, you know that if we have a good technology, then this M value is more or less close to number 1. So that's the reason why, roughly speaking, we can say that the change of surface potential inside our system can be related to the change of our threshold voltage. That will be our strategy. Okay, are you with me? So now think about this one. Let's say that this is a transistor, and assume that although this in this case the device is quite a short channel, but let's think about an extremely long channel device. Then what happens if we have an extremely long device here and there? Then everywhere in this case we will have quite similar channel properties, and now in this case we have quite much variation of our physical quantity along this y direction. That is difference between long channel device and short channel device. And think about this one. Happen to be, for example, drain voltage equal to 0 volt, drain voltage equal to 0 volt, and in this case we can define our surface potential quite well, and that will be almost uniform along this long channel device. But point is, understanding, qualitative understanding is, now let's assume that, okay, along this entire short channel device, surface potential is given as the long channel value phi sub s. Is this correct or not? Well, we have a little idea about the correctness of this assumption, but at least we can find this one. Well, think about this point. Is this really corresponding to the long channel surface potential? There are other different rules. This point is attached to our n plus source, and when n plus source, this highly doped n plus source is placed, and then more or less the potential is given as the value determined by our doping density. So simply speaking, I would like to say it this way. If I have to write down, then donor density is equal to our electron density, and this electron density is simply given by intrinsic carrier density exponential phi kBT over Q, summer voltage. So our potential will be simply determined by our m plus doping density. This is nothing, this value is nothing related with MOS structure. And now we have a contradiction. If this is regarded as a part of a MOS system, then maybe, well, since this is the surface point, so surface potential would be the right value. And if this is regarded as the part of M plus region, then, well, this should be corresponding to the doping dependent potential. And what is the contradiction? The contradiction is our assumption MOS-like system that is obtained from just one-dimensional vertical MOS structure. There is nothing outside there, and we just considered this x-directional system. This surface potential obtained from that way, so that is not very rigorous for our current calculation. Previously, when we consider a long channel, it was really justified quite well because source and drain are far away from the main body of our transistor channel, and what we can say is, at least for this part, the effect of a source and effect of a drain can be neglected. That was our assumption, and the channel part was just treated as simple MOS capacitor. That was the situation. But now we are talking about not this part, but we are now talking about this point, and this point should be regarded as a part of M plus source or M plus drain. So simply speaking, for this short channel device, now our assumption, well, long channel surface potential will be applied to entire channel. First of all, this assumption is wrong. We have to consider a different one, because this AB line is attached to the source part. So for AB line, we have to assign potential corresponding to the source potential. And how about this EF line? This line that is also attached to the drain, and the potential is corresponding to the drain potential, not the channel one. it's like this. There is a really large country, and there is another country, and here we have a capital city of this large country, and of course it has its law and culture, everything. And now we are talking about a village just at the border between this one country and the other one, and this is quite close to this small country. So, and now say that this capital city dictates that everything related with this small country should be banned, and you have to follow every rule following my own order. This is the case. Basically, this channel, and ideally this channel should be dictated by this, governed by this gate. So even though this AB line is quite close to the source, but ideally what we wanted to have is still this part, this AB line is governed by gate voltage. But unfortunately, well, this is just an ideal case. Unfortunately, this AB line is just attached to the N plus region. The real influence on this AB line from this source side cannot be neglected any further. That's the reason why we have to consider different boundary condition. So now think about other boundary condition. Here and there we have a boundary condition from source and from drain. And how about this BCDE line? Well, this white region is corresponding to the depletion between source and body, drain and body. And if you are studying the semiconductor physics, then you have to understand the difference between the width in this drawing. So source side drawing is narrower, and drain side depletion width is drawn a little bit wider, because we have assumed that positive drain bias relative to the source. So therefore the wider depletion region is assumed. And here let's say that this is the length scale. So depletion from source side and depletion from drain side, and what they do is more or less this length scale is just kept. So now we say that okay, maybe this is the amount of depletion obtained by this source side and drain side. Of course here we have also depletion part, and this part is actually determined by gate part. And please be careful, I'm not saying that this part and that part are completely determined by source and drain. No, it's not. Their behavior is actually governed by the collaboration between source and gate, or drain and gate, because this part is quite close to the drain and quite close to the gate. So this part is governed by these two different terminals. That's the reason why we call this part charge shared. The charge inside in this part is shared by gate and source, and shared by gate and drain. Okay. Anyway, let's come back. Now we consider a small box shown here, or rectangle box here, and CD is corresponding to the substrate, the border between depletion region and substrate. In this case, of course, we say that surface, not surface, but potential bending is just 0. Please note that when we say this way, phi equal to 0, we are already using the convention by Professor Tower. So the deep substrate potential is regarded as the reference potential. So it means that up to here, potential is just flat, and only in this depletion region we have a rapid increase of potential toward surface potential or other value. That is our assumption. Well, up to now, I have discussed some boundary conditions. AB boundary condition, that is determined by source terminal. EF boundary condition, that is determined by what? Determined by drain. And this guy is corresponding to the substrate. Since the substrate is grounded, that's the reason why we have 0. And of course, you can ask me this question. In this box, rectangle box, still we have open boundaries. How can we determine these boundary values? Well, let's think about them one by one. How about this topmost one? This topmost one is corresponding to our gate terminal. So its potential is simply given as VGS minus flat band voltage. If we apply gate voltage equal to flat band voltage, then there will be no band bending. So that was the situation we had at a flat band case. So by applying additional gate voltage, so this value is working as an overall potential difference across this MOS system. So simply speaking, this upper part, we have a well-defined value, single number for our top surface. Still, you can ask me this question. Well, now I understand all of these 4 boundaries, but still we have one boundary, another boundary, and also other boundary and other boundary. We have 4 still open boundaries. How can we determine them? So in this case, we introduce a simple rule. Well, we know value at this point, and we know value at this point, and inside or between them we have just MOS capacitor or pure silicon dioxide. So we just assume linear variation. I think that is quite much acceptable. And also, how about this GL? I'm not quite sure this is the no, FG1. That is also regarded as linearly varying potential. Yeah, this is not that bad in my opinion. Also, how about this BC and DE1? Well, this is not that quite obvious, but what we assume is like this. Please think about this one. Starting from this value, what is the value for our phi? Phi equal to 0. And what is the value at this point? Yeah, this point, the value is determined by our doping density. In this convention or in this notation, we say that this is corresponding to phi built in. What does it mean built in? So depending on the doping density in N plus region and substrate region, we will have the value. For example, here actually we will have minus phi b as a electrostatic potential, and here we will have the 1 nd normalized by intrinsic carrier density and take its natural logarithmic and say kBt over q. That will be the potential for our N plus region. The difference between them is regarded as, in our case, potential bending. So this amount of quantity is regarded as built-in potential in this case. So simply speaking, here in this notation, phi built-in should be regarded as phi b plus, well, blah blah blah, kBt over q length nd divided by ni. So now you understand all of this one. Of course, this phi b is still dependent on your acceptor density, p-type substrate. Now, between them, now you understand here phi following Professor Tower's notation, that is 0. And the one shown here is corresponding to the phi bi, built-in potential. And between them, we have just parabolic potential bending. So, are you with me? So now we have just a parabolic one. Of course, you can ask me this question. Well, it means that electric field is ever increasing when we approach it to this point. Yes, that's true. If we go to this metallurgical junction, then electric field, the magnitude of electric field is increasing, and we will have a maximum value at here. After that, inside this N plus region, within very short length scale, this high electric field can be neutralized. So are you with me? Because we are now talking about N plus P junction, whose doping density is Na, relatively low, and Nd much higher than Na. So we can just neglect depletion of N plus region. That's the reason why we can just consider parabolic behavior. So this is parabolic. This shows along this line we have the parabolic behavior. So what we can expect is, okay, along this line also we will have a parabolic behavior. Starting from 0, there will be just a parabolic increase of electrostatic potential. So just to follow the same consideration, so I'm not saying that this is rigorous, but what they do is, I think that this is a kind of real idea. Evaluating something or manipulating equations, that is quite known to all of us. Everybody in this room can perform this kind of job. But point is, when we have this kind of complicated problem, good researchers find a way to simplify this relatively complicated problem. What they assume is, okay, C potential equal to 0. B, still we have phi bi. So let's assume that the distance between this B point and C point are same to the source side depletion width, and let's assume that potential varies exactly the same way parabolic behavior. Following the same way, so even for this drain side, we say that distance between D and E point, that is corresponding to W depletion width in drain side, and we have a parabolic behavior. Then if we adopt all kinds of this problem, now let's just summarize the problem setting. Now we have, let me just oh, okay. So let me just explain the situation. So now we have a small box, and in this box, up to this part, this is attached to the source. Up to this part, this is attached to the drain. And here we have the part attached to the body. And between them, we apply parabolic behavior. Also between them, we have a parabolic behavior. And now we have oxidal region. And we know the boundary condition determined by gate. And between them, we assume linear variation. And we assume also linear variation. So now think about this boundary of this system. This system is now fully covered by the Dirichlet boundary condition. Everywhere in this boundary, we know well-determined value of electrostatic potential phi, actually reference to the deep substrate. And the equation what we have to solve for this system is quite simple. We must solve Poisson equation. In the case of a Poisson equation, unfortunately we have to consider contribution from electron, holes, and doping. Yes, doping is fixed. However, we must consider electron and hole contribution. But fortunately, in this case, the simplification can be done in this way. We will assume sub-threshold region. As much as we assume that bias condition, we can completely neglect the contribution from electron. Wow! Then how about hole contribution? Hole contribution should be considered. However, what we get, the simplification is this box, especially in this silicon box, also corresponding to the depleted layer. Then by assumption of this depletion layer, we have no hole at all. So by assuming these kind of approximations, now we can say, is there any electron? No. Is there any hole? No. Then only contribution comes from ionized oxygen density. So please note that in general we must solve nonlinear Poisson equation. It contains exponential dependence on the electrostatic potential in general. But by confine our region or area of interest by a clever way shown here, we can just solve linear Poisson equation. Since everything is just linear, its solution can be obtained relatively easier than non-linear cases. This is big advantages of that question. Then of course, please don't be fooled by this trick. The trick we should understand is actually this box itself. We love this B, E, G, H box. Within it, we can just solve linearized Poisson equation. But point is, this box itself is bias dependent. How did you select this B point? How did you select this E point? And how did you select this CD point? The definition of this CD point is, well, depending on the gate voltage, let's just say that if we have even higher gate bias, then what we will see is even further defletion due to higher gate bias. So we will have a further increase of depletion layer. And if we have the lower gate bias, then we will have the lower or shorter depletion layer. So the vertical position of this C and D, that is actually determined by the gate bias. So we never exactly know where C and D. Okay, so therefore, do not treat this treatment as a fully general, which is applicable for any general case. This position BCDE, that is actually determined by gate bias. When you change your gate bias, you will have a different BCDE point, and also depending on your drain voltage, so D point can be changed. For example, if you reduce the gate voltage, drain voltage, then obviously the depletion region will be reduced. So now you will have a much shorter this depletion region. So D point will be moved toward the drain point. So it is difficult to say this position is fixed to every case, but it should be regarded as some way to approximate the potential distribution at a given bias condition. Please do not trust this model too much. But anyway, I think that preparing this lecture material, I was really amazed by the cleverness of this model setting. So initially we have a very complicated problem, but by introducing some reasonable approximations, we were able to get much simplified model. Although it is simplified, but still it captures the physical essentials of this problem. So in the next lecture, we will try to find out the real expression for our simplified model. And where are you now? We are currently at lecture 16, and following our plan, actually we have to finish our discussion about this simple 2D potential solution, but we were not able to finish it. So in next lecture, lecture 16, we will shortly continue this discussion. After that, we will move to the discussion about velocity saturation. Okay, thank you.